Hi, everybody. My name is Avi from Xerox in Los Angeles. And I've been the antenna engineer with Xerox for nearly 11 years, almost from the beginning of the company. And I'm going to be talking today about antennas, antenna definitions, talking about some antenna designs, and later talking about some of the work that we do at Xerox. What we do in Xerox, and I'm just going to give a brief introduction. We've been doing access points that are multi-radio, multi-antenna types, up to 16 radios in a box. So we've been developing a multi-radio, multi-antenna access points. High performance, we try to maximize the performance of the antenna, all the RF section. Our products are highly integrated, so analog, digital, RF antennas all in one box, very compact, ceiling mounted in most of the time, and again, trying to achieve as high performance as possible. So I'm going to start talking a little bit about some of the terminologies and talking about certain antenna characteristics. And as in the previous lecture, when people try to do deployment, they make some assumptions about the antennas. And in real life, antennas has got a little bit more to them, a little bit other characteristics that are as critical as saying that what is the antenna gain or what is the antenna beam width. So we'll go through those too. Later, I'll be talking about some of the work, some of the designs that we have done at Xerox. And in general, maybe before I'll continue, I've been doing antenna design for nearly 30 years. I've done it for military applications, space applications. I've done it for the commercial market. And I more or less witnessed and been part of the evolution of antennas for GPS market, Wi-Fi, Bluetooth, RFID, body-worn antennas, and so on and so on. So I accumulated a lot of experience, and I'll enjoy conveying as much as possible and answer any questions. So let's go to the antenna fundamentals. I'll be talking about some of the characteristics related to antennas and RF. And so the first term is the dB. When we talk about amplifiers, about filters in the RF, about the radio, instead of talking about milliwatts and watts, about just numbers, if we have an RF chain and we have to calculate what is the power at the antenna, for example, we'll have to start to multiply numbers, divide numbers, or instead we convert everything to dB. So it's much easier to say, well, the radio is putting so much power in dBm, which is equivalent to milliwatts in dBs. We have a filter, which has a certain characteristics, including loss. So if we look at putting it all in an equation, we have the transmit power from the radio. We have an insertion loss from the filter, which is a negative number. We have an amplifier with some active gain characteristics. So we can more or less sum those together and know what is the power at the antenna. Now, the antenna can have a certain gain number that whether the antenna is directional or the antenna is low gain, that number over here of the antenna can change. When we talk about overall, the RF link, we talk about parameters like EIRP, which is we take the power output before the antenna, including the gain of the antenna, and that gives us a certain number that the FCC wants you to stay within, where the antenna gain needs to be within a certain window as well. When we talk about antennas, there are a couple of terms that are critical, and one of them is antenna gain or directivity. Directivity and gain are kind of related, only the directivity is the more ideal number that doesn't take into account some of the inefficiencies within the antenna. So the antenna has got main beam, will have side lobes and back lobes, but when it comes to the main beam, and we talk about gain and directivity, we talk about how the antenna focuses the energy in a certain direction in space. And we can direct it in any space that is of interest to us, where most of the activity is. When we talk about the gain, there's another term that comes right away into mind, and that's the 3 dB beam width. So that term comes up all the time when we say, oh, the antenna has got 30 dB beam width, the antenna has got 60 dB beam width. It's when we take the peak gain and we take 3 dB down, and those angles define where 50% of the energy transmitted is concentrated, but not only all the energy is concentrated in the main beam, because we've got other parts of the beam outside the 3 dB point. We have side lobes, we have back lobes. So it's not that we have a single beam, nice and clean, no side lobes, no back lobes. And so in practice, we need to take those into account. So when we talk about antennas, we talk about something that is the front to back. So we have a back lobe and we have a main beam. And the back lobe is a side product that has to do with the antenna design or with the size of the ground plane that the antenna is mounted on, or if it's an array, it's a byproduct of the array. It's part of the physics of the antenna. And not always we can avoid it. And the problem is, if the back lobe is too strong, and like previously mentioned, if you have some access points that are in close proximity to each other, that back lobe can splash energy in a direction that you don't want and create some interference with another array or with another access point that is operating on the same channel. So, we want to maximize the performance of our access points, and that back lobe can create a problem if we are not aware that the antenna is not just purely a single beam, but has got some other characteristics that we have to live with. Another parameter is the side lobes. So the side lobes, again, they are measured compared to the main beam, how low they are compared to the main beam. And again, the side lobes are a byproduct, whether because proximity or the antenna above a ground plane, or could be due to some obstruction, or it could be a byproduct of when you have an array. If you use panel antennas to get with a little bit more directional antennas, one of the byproduct of arraying elements together is the side lobes. And side lobes could be pretty strong, maybe only 13 dB below the main beam. And when you talk about a situation where you're dealing with almost 100 dB of dynamic range for maybe, let's say, plus 10, plus 20 dBm down to minus 100. And if the side lobes are that strong or the back lobes are only 13 dB below the main beam, they play a very important game. And again, they can splash energy in directions that are not aligned with the main beam. So again, that's another source for splashing energy in directions that you don't want to. We talk about propagation, and ideally, things may look at 2.4 kind of smooth at 5 gigahertz, but in reality, when we talk about propagation as a function, the signal strength as a function of distance away from the access point, we have dropouts. And those dropouts can happen at a certain interval as a function of the wavelength that we are working on. What happens at 2.4 gigahertz and what happened at 5 gigahertz, in a way, these are two different worlds. At 2.4 gigahertz, the wavelength is about 4.8 inches, where at 5 gigahertz, it's about 2.3 inches. So obstacles that are large or small can mean a big difference to wave propagating at 2.4 gigahertz or at 5 gigahertz. So an obstruction at 2.4 may be not a big deal for 2.4 gigahertz, where at 5 gigahertz it's a big deal because the wavelength is much shorter. And as we go higher in frequency too, from 2.4 to 5, other phenomena other than the space path loss, which is kind of a normal, this is the normal path loss, where we don't have any major problems with multipath, or in 5 gigahertz, we have scattering. Even if we are outside and we are shooting through a tree, the tree itself, the leaves of the tree at 5 gigahertz might add some scattering and diffraction phenomena, which adds to the overall signal drop or signal behavior as a function of distance away from the access point. So the sources for multipath, the classic sources, is when you have a source and it's pointed at the receiving end. And let's say it's got a gain that is moderate gain. But again, that antenna has got back lobes, it's got side lobes. So the energy, some of the energy is is reflected from a back structure, some side structure. And when these reflections arrive at the receiving end of interest, they might reach at where they are out of phase, 180-degree out of phase, and they're going to be one of the reasons they contribute to those dropouts. Those dropouts may become most significant as we are maybe in some very low levels, at some when the signal is very weak, and any small reflection might be canceling it. So sometimes you stand in a place, you move a couple inches back and forth, and the signal can change 10 dB and more quite easily. And so when you design products, obviously, when you design access points with the antennas, you try to kind of think about all those issues up front. And polarization. And that's an important term, and many people kind of skip over it. And why it's so important. In most of the time, when we talk about polarization, most people are used to talk that they sometimes don't even aware what polarization the antenna is. And so it's important, especially with directional antennas, that you co-polarize with your receiving end, even though the receiving end could be many users and not necessarily, if they are especially mobile units, the orientation of the mobile unit can be anything, and you cannot cover all of them. But in most cases, the antennas are singly polarized linearly, even though when we talk about some access points, they might be using more than one polarization. The problem is, on the receiving end, if you're vertically polarized and the receiving end is horizontally polarized, we might be seeing some mismatch or cross-polarization, and we might lose 10 dB easily. So some people in their access points provide both polarizations, transmit both vertical and horizontal, and that might be efficient to a point, even though, again, one of the polarization may be kind of wasted and not as effective as the other. Another solution, which maybe is not as popular, is circular polarization, where we transmit both polarizations, and they exist all the time with a certain relation between them. And so it doesn't matter how we orient our unit, what's the orientation, we're always going to receive it. It's in a way, we call it diversity too, in some way, like polarization diversity. So the idea is what makes the link as stable as possible. So even though on the receiving end, on one end you're circularly polarized, and on the receiving end you might be vertical or horizontal, so you might be losing some of the energy because it's both vertical and horizontal at the same time, or two vectors that are rotating at the same time with 90-degree orientation between them. But it's better to lose only 3 dB compared to if you're cross-polarized, if you're not oriented properly, you might lose 10 dB and more. So most people tend not to use circular polarization. It's like, I used it a lot in my previous life in the military world, in electronic warfare. It's quite popular. In the commercial market, it's not as much, even though in one of the new products that we are doing at Xerox right now, I'm kind of using it, and that's for a different reason, try to penetrate some real heavy, thick structures, walls, concretes, trying to increase the probability that energy will propagate through. And because there are rebars, and because there are different obstacles within the wall or within the concrete, that I'm trying to overcome or improve my probability for energy to propagate through. Another important term that is mentioned quite a bit is signal to noise. Depending on what data rate we are trying to achieve, what modulation scheme is being used, the signal to noise differ. And when we work in some very low data rates and one of the low modulation schemes, the signal to noise may be less than 10 dB. So it's very forgiving. But as we move to much higher speeds, higher modulation schemes, things needs to be just perfect. So the signal to noise might be 20 dB. So everything needs to be, the RF link needs to be tuned as perfect as possible. Everything needs to be linear, minimal distortions. Let's move to antenna basics. And I'll be talking about different antennas and showing you some examples. And so when we talk about transmit and receive, which are in a way interchangeable because the medium in the middle, the propagation space, is independent of who is to the left and who is to the right. The propagation medium is what it is, and it depends on the physical layout of that specific facility, indoor mainly, in my case. When we talk about range, when we talk about coverage, it's very important, and that's what we try to do at Zeros, is really try to maximize the performance of the RF link, minimize losses, so to control the noise floor as much as possible, at least within the access point, so that sensitivity is going to be in the maximum, because sensitivity is always has to do with the signal versus the noise floor. So at least within the RF link, if you control your amplifier, you control the insertion loss, the matching through the system, you can maximize the sensitivity of your system. When we talk about gain, we use a term which is isotropic source. And it's an ideal source. It doesn't exist in reality, but it's a case where from a point source, the energy propagates in all directions in the same rate. So in a way, it's a unity gain all the way around, and when you take it in dB, it's 0 dB. So when we say the antenna has got 20 dB, it's 20 dB relative to an isotropic source, and usually we say dBi to again signify that it's isotropic. Some situation people would rather make it relative to a dipole, then it's become dBd, or there are some other variations on that. One popular antenna is the monopole antenna, which is made of a ground plane and with a wire, a quarter wave resonator, and it's fed against the ground plane. So that antenna is very much dependent on the ground plane. So when we talk about, if we assume that this is the ground plane, equivalent to that, so as when we talk about antenna on a small ground plane, like in a mobile units, for example, where we have a very small antenna, then that beam width is actually, the coverage is more broad in elevation. But as the ground plane becomes larger and larger, that the shape of the elevation beam settles where the peak of the beam is somewhere around 25 degrees above the horizon. Or if the antenna is mounted against the ceiling upside down, so everything is just have to mirror image down. There are many variations of the monopole antenna. It's very popular in mobile handsets. But since the size is very critical, since for the antenna, especially in embedded application, so we start to bend the element, and that's what we create. We take that element, we bend it a little bit. We call it bent monopole, and sometimes it's not enough. We really need to make the antenna very low profile. So we really bend it down very close to the ground plane. And that's what we call the inverted F antenna. You might hear the term IFA or PIFA. And the problem is that as you make the antenna very low profile, which is nice, it fits physically into your design, but you start to shrink the antenna bandwidth, and you start to suffer from lower efficiency. The antenna is not as efficient. So if you try to transmit a certain power, a lot of the energy is going to be reflected or is not going to be transmitted. So it becomes an ineffective radiator, but in some situation, you don't have a choice because size constraints are the driving force. Some of you might see some other small antennas, by different companies like Murata, like Toco. These are ceramic antennas. They are very small. They're kind of nice because they fit nicely into mobile handset design, but not necessarily they are the most effective. People think that if they'll use it, they'll solve all their problems, but in reality, if we look at the data sheet, at the guideline, how to use them, we see that they require a certain ground plane because they are not really antennas themselves. They are just a resonator, and they need a ground plane to achieve a proper performance. So still, they're popular whichever way you look at them, whichever performance they've got, because physically they fit nicely into small spaces. The dipole antenna is another popular structure, but it's made out of two resonators, each quarter wavelength, and they fed 180 degree out of phase through a device, what we called a balun, which is unbalanced to a balanced network. And the dipole, like the monopole, is made out of 2/4 sections, so it takes more space. So even though the initial figure 8 on elevation, or the donut, looks like that, depending how much we squeeze it physically, that figure 8 might vary a little bit in shape, but still we always maintain OMNI coverage quite constant around. And the antenna, since it's what we call a balanced structure, because it's not fed against a ground plane, so it's less sensitive to nearby effects. It's a little bit more stable, but again, unfortunately, I couldn't use it in my design because it takes too much space unless I would fold the arms or do something physically to the antenna. And I'm going to show some of it later. This is an example I took it at a nearby UPS office. And so you can see it's a pretty scary creature. I'm not sure which antennas are being used, whether they are monopoles or dipoles. The thing is that in a lot of those designs, the antennas are external to the access point. But if they were not designed ideally, and in most cases, I can tell you that they are not, the feed cable connecting the antenna to the connector, coaxial connector on the motherboard inside the access point, that cable becomes part of the antenna. So many times, you're going to try to orient the antennas, and suddenly you're going to do some coverage measurement, and you're going to get some really bad dropouts, more than you expected. And the reason is because these antennas may not be that ideal. It's not up to you, but whoever decides to use certain antennas from a certain source, it's better to be careful enough to know that that design is designed properly. If the feeding, sometimes it's better to put ferrite on the coaxial cable that acts as a choke to minimize radiation from the cable, to make the coverage more consistent and less sensitive to the orientation of the antennas. Next, another antenna that is popular is the microstrip antenna. And the microstrip antenna is a very low profile antenna where you have usually we use a dielectric substrate. The antenna is at a certain length, usually a resonant length of alpha wavelength. And depending on the dielectric material that we use, the performance of the antenna might vary. But overall, it's an antenna with gain in the 3 to 7 dB gain, moderate gain, still quite a beam width. The microstrip antenna can be any of the polarization that we discussed, vertical, horizontal, or circularly polarized. And we can expand it into an array, and a lot of the panel antennas that you guys using in installations are based on that. And so when we array elements together, like shown in that figure, which is an 8x8 microstrip array, the gain is pretty high. It's about 24 dB. So usually my rule of thumb is that I design microstrip arrays up to about 24, sometimes 28 dB gain. But beyond a certain point, it's just trying to get more out of the antenna. You start to lose more in the feeding, all the feed network, which I'll show you here. So this design is really a stack design. So it's made out of 2 layers stacked above one another. So the first layer contains an array of 8x8 microstrip antennas with all the feed network for a dual polarized design. And then you have the parasitic layer, which is spaced at a certain distance above the first layer. And these patches are resonating at one frequency, and this, the parasitic layer is resonating at a different frequency. When you put them above each other with the mutual coupling between them, you get much broadening effect because you take 2 resonances and what we call the double amp solution. So we expand the bandwidth much more because at 5 gigahertz, the bandwidth is over 10%, where microstrip antennas tend to be much narrow band. So by staggering 2 different patches, one above the other, we can achieve much more bandwidth and still keep the design low profile. If we try to achieve more gain, it's much more practical to go to a reflector antenna because it's made out of a reflector and a feed, and you don't have to create an array with all the losses, all the inefficiencies within the feeding network. This is an example of pretty popular antennas for Wi-Fi, but for an outdoor application, for point-to-point, with gain in the close to 30 dB gain. And it's got a boom, it's got a dipole in a cup feed, but this is a grid design, so in this antenna is vertically polarized because the signal coming from the feed needs to be co-polarized with the grids. Otherwise, it's not effective. Reflector antennas are maybe not as popular for wireless communication because they more or less cover point-to-point situations, but in other markets, especially space applications, they are much more popular. Another way that, and we do it at Xerox, is when you try to increase your capacity, able to handle more, as many users as you can, instead of having one access point that covers a space, you can sectorize it with a certain overlap between those sectors. And if you're able to control the isolation between the sectors, you minimize what was discussed earlier, interference between radios. So that's something that all along at Xerox we've been trying to fight, and in every design this is the challenge that we face. By the better the isolation between the sectors, it enables the radios to operate within the same band, let's say 5 gigahertz, and we can do better frequency reuse that radios that may not be nearby, but radios that are within the same box. In our case, they can operate at the same channel and still not interfere with each other. By doing that, the access point is the capacity, the ability of the access point to handle as many users as possible in a given space grows. So makes the deployment much more efficient. You can minimize the number of access points that you need to use in this way. this is one of the old designs at Xerox, and you can see that always you have a radio, in our case at least, we have a radio and an antenna, and it's broken into sectors, and in between the sectors, we tend, at that time, use absorbing material that help to minimize any splashes that are due to side lobes and unwanted radiation coming out of the antenna. So by adding those absorbers, you kind of control the isolation. We have a magic number. I have a magic number where I want to be, and usually at 5 gigahertz, I'm trying to keep the isolation between the antennas, the physical isolation, just between the antennas, nothing to do with the radios, at about 40 dB at 5 gigahertz. If you take that 40 dB and you add to it channel selectivity, and there's certain things you can do in the software part, and you can get to a situation that if you can control the ends of the power at the ends of the link, you're able to achieve a situation where the radios are working in peace with each other within the same box, and achieve as good capacity as can be done compared to a mesh network deployment. So I'll be talking about some of the antennas at Xerox, and that with some photos that will give you some idea. So in the last couple of years, the antennas, oh, I'm sorry, not the antenna, the overall design of the product, instead of trying to have a motherboard with all the RF on it and the antennas, I rather came out with a modular solution, and I'll try to show it in this case, where you have a radio card that is made of the RF part of it, which is that part. That part contains the radios, all the matching network, and then you have the antenna portion or the antenna section up here in this area. And the nice thing about it is that when we have a 2-port or a 4-port or 6, 8, up to 16 port, we use the same building block, which is that module. So it's kind of nice because we use that module all across the product lines, at least for the high-performing product line. So in our case, one second. Let me go back. So those radio cards can be for 2x2 with 2 antennas, 3x3 with 3 antennas. And it doesn't matter if you go to the extreme case of 16 cards or 16 port, the isolation where they are within 1/10 of an inch from each other, they still maintain 40 dB isolation at 5 gigahertz. And all the antennas, all those cards are always dual band, so it enables the radio to switch bands from 2.4 to 5 or vice versa on the fly. So an example in those radio cards, this is how an antenna look like. And it's a two-sided, so I'm showing the 2 sides of the antenna. It's printed on a circuit board material. This is what we call a Vivaldi notch type antenna. So that feed excites the notch. So that section operated 3.5 to 8 gigahertz. And unfortunately, because I squeeze everything is bent. The ends here at 2.4 gigahertz, these are the extra resonators to make the antenna resonate at 2.4 gigahertz. So you can see everything is folded, everything is squeezed in order to fit it within a given space. And the way we use it is we have in the antenna section, and maybe it's hard to see, but there's a reflector here, which is a bent piece of metal. So one antenna is mounted here, the other one is mounted here. This is a 2x2 case. So what I'm doing is I'm trying, when we have multiple channels in a MIMO situation, it's not going to be efficient to have all the antennas pointed in one direction. So rather I'm creating more like a space diversity. So when this antenna is shooting an energy more in that direction, this antenna is shooting more energy in that direction, and the beam width is about 60 degrees. So it's kind of directional, not that directional. But overall, I'm getting two beams that are overlap each other enough. So the overall look angles from that module is you take those two beams together, you might get coverage of 120 degrees, 120 degrees. So the illumination is quite efficient. The gain is very efficient. And in other applications, we can continue with the same idea and create a 3-channel design. So you have now 3 antennas. One looks at the center, the others to the side. So again, you get a very efficient illumination and gain in the 4 or 5 dB, which is kind of nice. Same thing, you have the reflector in the back of the antennas, and those two corners, the two corners that we've got here of the reflector create what we call corner reflector antenna, which is a very old popular design for low frequency. It's very challenging to do it overall because it's a narrow band phenomena, but if you look on the other side, which I'm not showing, there are some other tricks that I'm doing in order to make it broadband or dual band, to work both at 2.4 and 5. And actually, that's one thing that I later improved when I went to the 11AC design. So for the 11AC design, one of the issues is at 2.4, because the reflector is small, it was very difficult to achieve enough gain. At 2.4, 5 gigahertz was pretty good. So this is the antenna element, at least one of the antenna element. But overall, what I'm doing is I create what we call a Yagi effect. That is another popular term. I wouldn't say that I'm using the Yagi design, but I'm using a Yagi effect. So I have 3 antennas. They're not working that good at 2.4, so I'm trying to get a little bit more juice out of the antenna. So more or less in that intersection point, which is more, it's strategically more or less an optimal space from the antennas to that point, I position what we call the director. So in a Yagi antennas, you've got reflector, you have the driven element, and you have a director. So in this case, for the center antenna, the center antenna in this case, this is the center antenna. There is an additional director, and that director is frequency dependent. So what it does, it makes the antenna, the center antenna, and all the other antennas as well, see it as a dual polarized director. Very unusual. There is a patent that I'm getting on that. I don't think anybody have done a situation where one director can be shared with multiple antennas. The overall effect is really, really good. I'm able to enhance the gain at 2.4 by a couple of dB. So now I'm getting that radio card that over here works really good at 2.4 and 5 gigahertz. So it's a very efficient solution. This is an array in the 11AC 8-port. So you can see 8 cards populated and in an enclosure. And what we do is in the spaces where we don't have cards, we put conductive gasket so that when we put the cover over that structure, which is metallized, we can enclose all the electronics within like a Faraday cage and minimize emission coming out of the electronics. So again, trying to do whatever we can to minimize any source of distortion, anything that might affect the performance of the antennas, because sometimes those emissions, if there is not a proper shielding, they can do that. Same thing, you can see a 4-port device using the same cards, using the same idea with the conductive gasket, and then having the cover with the shielded part of it and closing it and creating a Faraday box. Another challenge that started a year ago was to create access points, very low cost, and not with the radio cards, as something low cost. So in this case, the idea was the people that were interested in that product, we still wanted good performance, good gain, having good isolation between the radios. So we came out with a product that looked like that. This is what we call the XR630, 620. There are two radios in that array, and could either work in a 2x2 or 3x3 arrangement. The problem is it had to be OMNI. So what I've done there, first of all, this is the antenna element used. It's kind of a broadband monopole, and it's being used needs to be mounted on a motherboard in a pick and place SMT process. So it's got a tab that the machine picks it up and places it in the proper place. In the final design, I don't have those tabs. That's the feed point. So it's placed, soldered in place, and ready to go. And this is the 2.4 portion. The rest is the 5. The beauty of that design is it's got some directionality to it. And as I'll mention later, it's got some, it helps me to achieve same isolation numbers that I've been achieving with our other products. So what happens here is that in this case, it's a 3x3. So imagine yourself that you can see 6 monopole antennas, but as I mentioned earlier, I'm putting it against the wall, so the energy is splashing down and to the side. Which, unlike the dipole, the energy is pushed down. And the beauty of it, what I'm doing here, is that I'm creating what we call an interleave arrangement. So I'm taking that antenna, and that antenna, every other antenna, this, that, and that, connected to one radios, and the other ones, the other group, to another radio. So the isolation between any antenna is 40 dB and better. So the isolation between the radios is still really, really good, and they can operate with the proper power levels in peace with each other. At the same time, creating that kind of an arrangement helped me to achieve really nice, clean OMNI coverage, and with very minimal interference or any distortion. And the PCB itself is used as the ground plane, and gain-wise, I'm able to achieve gains in the 4 dB, and this is a relatively low-profile access point, so it's kind of nice. Works really well. So this is kind of the end. I'll be glad to. I could talk about antennas for hours and hours. Yes, please. Something.
Do you have any examples of circular polarized antennas that are mainstream in Wi-Fi solutions today?
I'm using it. So imagine yourself that if we were to go back to, I don't have here examples, unfortunately, but if we were to go back to the dipole case, so imagine yourself that if you had a dipole, two dipoles, one dipole is in that direction, the other dipole is orthogonal to it, and you fed them at 90-degree quadrature, you would achieve that. And I could send you a photo if you want. I could send you, show you how it looks like. There are many forms of circularly polarized antennas. And again, most of the people in the market, not only, I'm not talking Wi-Fi market, I'm talking even within the antenna world, they kind of afraid to get into it. It's I don't know, maybe because I've done so much work in that area, I'm very familiar, I'm very comfortable. And the problem is when you use circularly polarized antennas, you have to use a hybrid involved. So, but it's not, there's nothing difficult about it. Actually, I found it that it can add a lot of more power. And I'll be able to tell you in maybe a few months how successful I was with that new product that we are working on, how well it works. Again, the idea is that circular polarization will help you to increase the probability that you could go through obstacles much more efficiently, because you add a lot of flexibility to the antenna, to that energy, electromagnetic energy, that will enable that if one polarization suffers, the other one will cover for it. Because overall, what we want to do, what we can do on the access point, try to come with antennas that will smooth things, that will minimize dropouts as much as we can. Some of it has to do with the way we install things, but we try in the design to provide as smooth, as consistent coverage as we can. So if you think about all those, what could be the factors that kind of could create more distortion or more dropouts, it's nice to think about that up front and help the guys in the field with their deployment. Oops.
So you started talking about small form factor antennas and monopoles, and the first place that my brain went was my iPhone or a laptop or some other consumer product.
Yeah.
And that's one area that, as a Wi-Fi professional, I don't have a lot of information or control over. Is there any one detail or one specific piece of information about consumer or client antennas that you can think of that would help us just in our daily lives?
Yeah, honestly, very difficult, because with a lot of those designs, there is a lot. First of all, in an answered, you've got multiple antennas, and the phone itself is metallized. So there are certain areas within the phone that you can radiate energy, and the efficiency is not that good. In the case of cellular band, the efficiency of the radio with the antenna is only 20-something%. So if you transmit 1 watt, you might be only really transmitting 200 milliwatts effectively. So very inefficient. And so the antenna guys for example, at Apple, I don't want to be in their position because I'm sure that they're being pushed quite a bit to come up with antenna solution to fit within a given space, and a very difficult environment, especially when they came in with the iPhone 4, where it was a pretty good idea where they placed the antenna on the outer skin of the enclosure, because less interference with anything nearby. They were using part of the battery clip as part of the antenna. The problem is, I think they were probably pushed a little bit time-wise, couldn't maybe optimize it properly, and unfortunately the market, the product came out to the market and there were problems because of the antenna. So there are some, you're going to see there are a lot of small antennas out there. Again, ceramic loaded, very small. When you look at them at the first look, you might say, ah, yeah, they look good. In reality, again, the environment inside the phone, the smartphone, everything is so tight, nothing is ideal. So there are a lot of compromises. And every phone, I'm sure because of the combination of the form factor and the antennas on it, has got different coverage, different sensitivity. Don't forget that in addition to all of that, there is a certain, what we call the SAR numbers, certain absorption that you have to meet. So you walk in a very tight world in order to meet all the constraints. So it's not an easy environment. So in most cases, you would think that you better rely on a good access point than on your phone to provide the superior performance that you need. So unfortunately, you have to, when you use your handset, you kind of have to, if you understand those constraints, you kind of know how to maneuver a little bit. But if it was my choice, I would rather use the antennas that were external to the handset. Unfortunately, I think psychologically, people that don't see the antenna, they think it doesn't exist. I think the majority of the public, when they see a handset that nothing sticks out, that means that there are no antennas, there's no danger to radiation and absorption by your head and any of that. So it's kind of, you live with the constraints, unfortunately.
Well, thank you very much, Avi.
You're welcome.